All right, this lecture is going to communicate rising air, relative humidity, dew point, and how it applies to adiabatic processes. So when we talk about adiabatics, we're going to be saying that ascending air, air that's rising vertically, is going to be cooling, and therefore air that's subsiding or moving downward is going to be heating up. So let's start with a review of what we know. Humidity is the amount of water vapor in the air. That saturated air is completely filled with water vapor that is at its capacity and can hold no more. Capacity is temperature dependent. We can see that here. Warmer air can hold more water vapor, and therefore colder air can hold less water vapor. And that when we increase or add, when we have water itself, is going to be adding pressure to the air. We need to keep in mind what a mixing ratio is. The ratio is the mass of, or the mixing ratio is the mass of water vapor to the mass of the dry air itself. That the mass of water vapor in a unit of air compared to the remaining mass of the dry air. So we've got this ratio, and it's measured in grams per kilogram. So we've also defined relative humidity. It's the ratio of the actual water vapor content compared with the amount of water vapor required for saturation at that temperature, and technically at that pressure. It's expressed as a percent. It's a percent. It's the water vapor capacity, water vapor content divided by capacity. And saturated air contains equal capacity. The content, water vapor content, is equal to capacity, and it has a 100% relative humidity. So if we look at daily variations of temperature and relative humidity, that just before sunrise, when temperatures are the lowest, we're going to have the highest relative humidity. And that in the mid-afternoon, when temperatures are the highest, we're going to have the lowest relative humidity. It's simply because the water vapor content can be the same, but the temperature is going to determine the capacity. So relative humidity can be changed two ways. We can add or subtract moisture, the water vapor content. That adding moisture increases relative humidity, and removing moisture decreases relative humidity. And in this picture here, I can show you, I can actually enlarge that. That if I have temperature is constant here, 25 degrees C, it has the same capacity. That 5 grams is only going to be 25% relative humidity. But if I increase that to 10 grams, it's going to have 50% relative humidity. And if I have 20 grams, it's going to have a relative humidity of 100%. In other words, 25 degrees C can hold 20 grams of water vapor. And that the amount of water vapor here, 10 over 20 is 50%, and 5 over 20 is 25%. So we're looking at a proportion, or the ratio. The second way we can change relative humidity is change the temperature. Lowering the temperature increases relative humidity, or raising the temperature decreases relative humidity. So here's the picture we can make sense of. We're changing the temperature here. So here's a larger picture. So here I have 20 degrees C, and let's say I have 7 grams of water vapor content. Well, the capacity at 20 degrees C is 14 grams, so 7 out of 14 is 50% relative humidity. Where at 10 grams has a capacity of 7 grams. So if it contains 7 grams and its capacity is 7, it's got a 100% relative humidity. And even cooler temperatures at 0 degrees C can only hold 3.5 grams of water vapor. If it has 3.5, its relative humidity here is 100%. So there's two different ways that we looked at. We can change the amount of moisture, or the water vapor in the air, or we can change the air temperature to change the relative humidity. And that brings us to dew point. The dew point temperature, this is the temperature in which a parcel of air would need to be cooled to reach saturation. That cooling the air below the dew point causes condensation. We can create dew, fog, cloud formation. We're essentially saying that water vapor requires a surface to condense on, or which we're going to call a condensation nuclei. And that's why when we create a cloud in that little cloud chamber, that plastic container, we need to put the smoke in. That's going to provide the nuclei, the condensation nuclei, as it provides the dust or the aerosols in which to condense the water vapor around. So we're going to move into a couple questions. So what happens to pressure and altitude, or pressure as altitude increases, and what happens to temperature? So we can look at these graphs here. If you notice, if we move up in altitude or elevation, we're decreasing pressure, right? We're going to continue decreasing pressure, and temperature decreases as well. Therefore, as we talk about air that is descending, pressure is going to be increasing and temperature is going to be increasing as well. So now we can look at stability of air. Stable air resists vertical movement. It doesn't want to move up or down. Warm air that is rising will continue to do so while cooling until it reaches an elevation that becomes equal to its surroundings. This type of air is considered unstable. Stability implies a parcel of air has a tendency to stay in its original position. Unstable air rises and weather phenomena occurs based on the conditions of the parcel of air interacting with the surrounding area. So here's a few terms that we're going to make sense of here. The term ELR is the environmental lapse rate of 5 degrees C per 1,000 meters. In the adiabatic lapse rate, we have both dry conditions, it's air that's rising or subsiding, that is dry, that is below its dew point, is going to change its temperature 10 degrees C per 1,000 meters, which is the same as 1 degree C per 100 meters. And wet, meaning if it's at its dew point temperature, it's going to cool at a different rate of 5 degrees C per 1,000 meters. Stable air is where ALR, the adiabatic lapse rate cooling, exceeds the environmental lapse rate. And unstable air is going to be where the environmental lapse rate cooling exceeds the adiabatic lapse rate. So let's apply that. Dry adiabatic rate is unsaturated air. Rising air is going to expand and cool at 1 degree C per 100 meters, or 10 degrees C per 1,000. And descending air is going to compress and warm at the same rate of 10 degrees C per 1,000 meters. That the wet adiabatic rate is going to commence at the condensation level. This is what we can call the cloud line. This is when the air has reached its dew point. Condensation is occurring and latent heat is being liberated. This changes the adiabatic rate. Heat released by the condensing water reduces the rate of cooling. We looked at phase changes. As water vapor condenses into a liquid, it gives off 600 calories per gram. That's going to influence the temperature change of the adiabatic cooling. So now we can look at 4 processes that lift air. And the first one's an orographic lifting. This is where we have some elevated terrain that acts as a boundary or a barrier. We can say a mountain range. That the results can be a rain shadow desert. Here's what we have. We have these original or initial conditions of 25 degrees C and a relative humidity 50%. As it comes into contact with this orographic boundary, it's going to be lifted. And as it rises, it's going to adiabatically cool. It's going to cool at the dry rate until it condenses, until it reaches its dew point, and then clouds are going to form. It's going to continue rising, and it's going to get rid of, dump out the excess moisture. And then it's going to move over the boundary, and it's going to subside. And it's going to heat up at the dry rate. The second process that lifts air is what's called frontal wedging. It's really involving a warm front. And this is where warm air is moving aggressively towards cold air. That the warm air is moving faster than the cold air, so it's going to override it. And in the process, we're going to see adiabatics taking place. And we see a trend of warm air rising above the colder, cooler, denser air. And as a result, the warmth, the moisture in the warm air is going to rise and condense into clouds and generate rain. And this takes place in mid-latitude cyclones. The third process that lifts air is called convergence. This is where air collides. When we have converging winds, it can only go one direction, and that's up. In the state of Florida, which is what we see here, we have converging winds. It drives upwards, and it creates these very powerful but very short-lived storms. So when airflow moves into one another, lifting results. It has nowhere else to go. When air flows in from more than one direction, it has to go somewhere, but it cannot go downward. And that's why Florida has many afternoon storms as a result of this very process. And lastly, the fourth process that lifts air is called localized convective lifting. Convection. Localized convective lifting occurs when unequal surface heating causes pockets of air. Literally, this like bubble of warm, moist air is going to rise, and it's going to cool adiabatically. And this is going to rise because of its buoyancy. The warm material is eventually going to rise, it's going to reach its dew point, and it's going to continue rising, and it's going to generate a very short-lived kind of a pop-up storm that we get in the summer. And they normally kind of come and go, but convective lifting. So the 4 different processes that lift air is orographic lifting, frontal wedging involving warm fronts, convergence of air that's colliding, and convection localized.